have Marcus from Lier-Walqui. I never know how to pronounce it.
At least you know the first part.
The Dutch part I know how to pronounce. But so he's been here about a year or so working for Anna and Andy. And he came from the city, Miami, before he did his PhD. So, take it away.
Okay, so I'll talk a little bit about some of the research that we're doing, looking at polarimetric radar and deep convection. Let me just think for a second, or think and talk at the same time. And specifically, observations collected during MC3E, which is the Department of Energy ARM program's Midlatitude Continental Convective Clouds experiment. I think I got that right for the first time. So I'm gonna, for people who aren't like super familiar with polarimetric stuff, I'm gonna give a little background. And if you went to my talk that I gave last year here, it's going to be unfortunately repetitive, but the rest has some new data that I'll show. Okay, so motivation. Well, radar is one of our best bets for getting data about cloud and precipitation features. And why? Well, we can get a three-dimensional scan with scanning radars. They usually have pretty good temporal resolution, however you define that. Certainly compared to something like sounding, we have extremely good temporal resolution. And we have this beautiful nationwide coverage with NEXRAD radars. And certainly you can think of something like GPM or CloudSat providing global coverage. Okay, so there are certainly limitations, and one of the main limitations is that the number that we get out of the radar reflectivity, doesn't really give us the information we necessarily want about clouds and precipitation. So what sort of information is that? Well, we want to know the phase of the scatterers, ice, water. What are we really looking at? Are we looking at something that's neither ice nor water? Maybe it's a bird or a plane or Superman. And also something like the mixing ratio of the scatterers. So you know, how many kilograms of water do we have in a kilogram of air? Or the number concentration, how many particles do we have? So these are all things which are related to radar reflectivity, but they're related in a non-unique way, and the single variable that we get out of radar reflectivity doesn't allow us to discriminate between all three of these, or any number of other variables that might affect that we might be interested in. Okay. Oh, and of course we're interested in the microphysical processes that are happening inside of the cloud. Exactly how are hydrometeors combining to create snow, rain, hail, and so on. So we really want to get some insight into those details, but radar reflectivity is limited. Of course, how can a single variable really tell you everything in any case? So let me just go, well, now I'm going to skip this. So I'm going to skip this. I basically already said all of this. Okay, so the main idea behind polarimetric radar is that, well, traditional radar, you transmit a horizontally polarized radar wave. It scatters off of stuff, and then that return comes back, and you measure basically the horizontal polarization of the return. And the main idea behind polarimetric radar is to transmit and receive both horizontally and vertically polarized radar waves. The polarization is determined by the electric field. Of course, the magnetic field is orthogonal to that. All right, and then what's compared is the horizontal and vertical returns. So this can tell you information about the shape of the particles that you're looking at. How they're angled, whether they're ice or liquid, and more information. I'll get into that a little bit. And just in case you don't know, the National Weather Service upgraded all of the United States NEXRAD radars to polarimetric capability in 2013. I think the first one is actually the radar, the NEXRAD radar I'm going to be showing here was actually the first one that was upgraded. So trivia if it comes up in a bar quiz or something like that. Okay, so just an example of why this is important, why looking at polarization is important. So basically, these are raindrops. These are photographs taken of raindrops. And as size increases, and then it continues increasing here, you can see that the raindrop shape becomes oblate, becomes wider in the horizontal than in the vertical. And so what this means is that the scattering cross-section is greater in the horizontal than in the vertical. And if you compare your scatter back, your back scatter, it's going to be different for a horizontally polarized beam or a vertically polarized beam. So, well, you can then imagine that if we have a bunch of small droplets, they're going to look very different than a few large droplets, even if they have the same reflectivity.
Excuse me.
Yep.
This is going to be recorded, right? I could just
Yep.
check it out later.
No, ask questions, please.
No, it's okay.
No, please.
No. I think I'll just check it out later on mine. Thank
But
you.
then, no, ask a question, please. Ask any questions.
No, from what you said, I don't have any questions. Thank you.
Okay. You know, when we get to ice, it gets more complicated. You might have sort of traditional snowflakes, which are these snowflakey-looking things here, which might be more horizontal. They might fall kind of like that. So they might be have a greater cross-section in the horizontal than the vertical, and this might show up as a signal. These things might show up differently, and various ice crystals, whether columns or plates, can also show a unique signal, perhaps. Okay, so getting into what sort of stuff we get out of this radar, one of the variables is this ZDR, which is differential reflectivity. So this is basically comparing the horizontal return. So if I send out a horizontal beam and I get back a horizontal return, comparing that to the sending out a vertical beam and getting a vertical return. So that's basically what this shows. You're just dividing, taking the ratio of the horizontal and the vertical. And here we have helpful ZDR factors that you might find for these sort of shapes of water droplets. And then if you think of something like hail, well, even if hail is kind of lumpy, usually when it falls, it tumbles. And so you're not really going to get a preferential axis. So usually here the ZDR is going to be close to 0. So this is one way to tell between having hail and having rain. In both cases of heavy rain and hail, we're going to have high reflectivity, right? That just means that we send out our signal and a lot of the signal bounces off because there's a lot of stuff to bounce off of. But in the case of hail, our ZDR is going to show 0, whereas our rain is going to show some high value. So if we see high reflectivity, low ZDR, we say, oh, we're looking at hail. So this is very useful. Okay, so right, as I mentioned, it's sensitive to this oblateness. So it's related to the rain size and N naught if you care about that. It's insensitive to concentration. So because you're taking a ratio of these reflectivities, it's not as closely related to exactly how much you have. And this can be affected by attenuation. So with some radar frequencies, you're going to get your signal cut out by, it's going to get attenuated by the scatterers. And ZDR is especially sensitive to this. The differential attenuation can really mess up this measurement. Okay, so there's some other things that we can look at. This is another very important one. Phi dP and KDP, which is differential phase and specific differential phase. And so basically what you're looking at is as your light wave passes through various scatterers, the phase is going to be shifted. The wave is just going to be shifted a little bit. And it's going to be shifted differently in the vertical and in the horizontal for the same reasons that we have differential backscatter. So if we compare these, we can sort of see regions where the phase is getting shifted. So you can see that it's a cumulative thing because the phase gets shifted more and more and more and more and more and more and more. But if we look at just where the phase is getting shifted, we start to highlight certain regions. And these regions are important because these are regions with basically a lot of liquid water. So that's one interpretation of this, is that regions where you get a lot of specific differential phase shift is where you have a lot of liquid water. So you can actually use this to get estimates of rain rate. So for that, this is a very important variable. Okay, so similar to ZDR, it's sensitive to ablate particles. It's insensitive to attenuation, so that's very useful. If you're using a radar frequency that gets attenuated a lot, then phi dp and KDP might still be useful variables. It's sensitive to rainwater concentration. If you're trying to estimate how much it's raining, this is a very useful variable. And just to be clear about the relationship between KDP and phi dp, KDP, what's shown here, is a range derivative of phi dp. So if I take the derivative sort of along the line here, then I get that.
Marcus?
Yep.
When you say these regions indicate a lot of liquid water, but that's a lot of rain. A lot of ablate liquid particles.
Right. Because if we have a lot of cloud water, they're not really going to be sensitive to that. You're right. So exactly, it's really I'm more clear in my slide than in my words. Sensitive to rainwater concentration. Okay, so here's another polarimetric variable, and the copolar correlation coefficient. Basically, you're looking at the correlation between your horizontal and vertical returns. And basically what this is going to tell you is how much of a mix of scatterers you have. So if you have a big mixture of scatterers, you have rain, you have hail, you have birds, you have cows, then you're going to have a low correlation between the signals, right? Whereas if you have all one type of scatterer, it's all rain, it's all snow, then you're going to have more correlation between the signals. So this is useful, for one, for picking out non-meteorological scatterers. If you have something, you're like, what is that? Is that rain? What is this big rainstorm coming? And then you look and the ρHV is very low. Well, maybe it's actually birds or insects. Or in this case, it's very useful. This is velocity here. And if you've looked at velocity, these sort of velocity plots for, this is radial velocity. For a tornado, this is typically what you find. You find a very high velocity and then a very high negative velocity. I hope I got that right. Positive and negative. Is the other way around? Anyone know? In any case, what you basically have is something spinning. So you think, okay, maybe there's a tornado here. But a lot of times you don't know for sure. Because you can still get this signal and not have a tornado actually touching down. Well, if we see a big drop in the ρHV, what that's telling us is that likely there is a tornado on the ground and it's kicking up a lot of dust and debris. So that debris is going to have a very low correlation between the horizontal and vertical returns, and we see that as a big dip there. So we can forecasters can confidently say there's a tornado on the ground.
So, so you correlate at different heights? Is that what do you correlate with? At different locations?
I think it's within a range gate. You correlate just the raw signal. I'm not exactly sure. This is the limit of my knowledge.
Within the time, within the integration time.
Right. Within, I think within whatever the integration time is of that results in your radar gate. And I'm not, the specifics of this is the one that I feel least confident about explaining. So I can point in the direction of better authorities on this. Okay, so can indicate mixed phase or clutter, and can identify a melting layer or tornadic debris. So in the melting layer, you have melting snow and ice, which is then mixed with rain. droplets or coated water particles. So you'll see a dip in rho HV there as well. So
I have a question.
Yeah.
What do you mean by debris? What is debris?
Debris?
Yeah.
So like dust or dirt or pieces of vegetation.
Okay. If it's like dust in aerosol, then I'm thinking that depends on their size. It can be high, but I was just curious whether some of this signal is actually contaminated by aerosol.
I doubt it because I don't think aerosols would measure appreciable values of backscatter. At these frequencies, I don't think you get enough of a return off of just aerosols or even coated haze particles or anything. Radar will just cut right through those. So it indicates a lot of debris that is sensitive at these frequencies, which has to be considerable debris, the sort that will only be lofted by very high winds.
Okay. Okay.
What is the wavelength?
So this is probably NEXRAD, so 10 centimeters. And the sort of value, the ranges that might be meaningful will vary depending on what frequency you're using. This is actually a C-band, so the range is greater than for NEXRAD, where you'd be looking at a smaller range. In any case, so this plot shows a melting level where we have depressed rho HV as well. And this is, I'm sorry, this is vertical and horizontal. All right. So basically the experiment that we're looking at data for is there should be an MC3E here. Midlatitude Continental Convective Clouds experiment. And it ran in the late spring, early summer of 2011, in and about the ARM Southern Great Plains site, which is here in northern Oklahoma and southern Kansas. So over here is Oklahoma City. The ARM has a big site here which has lots of instruments. There's radars here. Here's a C-band radar. That's some of the data that we're looking at. There's X-band radars, 1, 2, 3 X-band radars. Here's the Vance NEXRAD radar. So I'm looking at data from that. And I believe there's another NEXRAD radar here and another one down here. So there's a lot of data, and there's sounding sites here and also a central sounding site and increased frequency of soundings throughout this period. So that's kind of the data we're looking at. So here's the NEXRAD radar, the C-band ARM radar. We're also looking at 3 Doppler wind retrieval, so using 3 radars to get a 3-dimensional field of winds. And we'll eventually be also making comparison to high-resolution model simulations using bin and multi-moment bulk microphysics. I don't have anything to show you with that because that's still in the process. Okay, the days we're looking at are the following 4 days. So we have 2 days, the April 25th and May 20th, which are kind of squall line days, and I'll show you what those look like. And then the 23rd and 24th, which are supercell days. And I'll show you what those look like also right now. So I'm sorry that this isn't larger. I actually, on purpose, made it smaller so that it would fit the screen, but I made it too small, I suppose. So this is the April 25th. And you can see there's a line of convection which kind of enters the region there. And the reason I have limited time is I'm just matching it to the data that we have from the C-band. Okay, so this is reflectivity. This is sort of what's usually used, a non-polarimetric product. Differential reflectivity, it's a little bit hard on this color scale to see what's happening. I'll show you on a different day something that looks a little bit clearer. KDP, that's the differential phase, and rho HV. So don't worry about that right now. I'll explain maybe here with the 20th. Might be a little bit easier. So the 20th is another squall line day, and it starts off with some scattered convection, which then quickly organizes into a bow echo, So you can see that here. And then there's trailing stratiform. So we have the sharp line of convection, and then the trailing sharp line of strong, heavy rain and convection, thunderstorms, and then the trailing line of more moderate rain. Okay, and if I just pause this at an opportune moment, let's say right there. Okay, so one of the things that you can see, you have high reflectivity, and in those regions also we have high ZDR, which is telling us that we have large water droplets, or rain droplets rather, and we also have regions of elevated ZDR. In the stratiform region, I don't know if that's from melting snowflakes or other processes. For KDP, we have indications of very large amounts of liquid water along this line, which we'd expect with this heavy convection. It'd be like a heavy downpour, and as well as some here. Rho HV, it's a little bit harder to pick anything out of that.
Seems like there's a lot of artifacts.
So there are artifacts, and part of the reason why there's artifacts is this is what I'm showing now is a horizontal slice of gridded data, and that's gridded from this the raw radial radar data. At this point, so you can see that there's kind of a circle there. Yeah. You switch from the super resolution radar scan to the regular resolution radar scan. So NEXRAD right now, they have these new super resolution scans, which are only for the first 4 levels, and then above a certain elevation it goes back to regular resolution. So because of that, when you grid it all together, you get some artifacts around that region, and you also get these rings produced by gridding data, which has been processed radially. So the specifics of how you get differential KDP specific differential phase from the raw differential phase kind of explain some of those, but I don't know. If you're interested, I can explain it a little bit more. But
is there a way to remove those or so? Because it seems like if you do statistics or so, I don't know.
You can smooth, I suppose, and you can, so the way that the KDP is derived is basically on each scan. So on each direction or each angle and each elevation of the scan. Mm-hmm. So you process it along that line, and you do each of them independently. So there might be some variations that result in sort of between each angle getting a slightly different result, and you get artifacts based on that. Yeah. You could try to look for a global solution, I suppose, to that problem. Instead of optimizing along a single line, you'd optimize globally, but I think that would be computationally prohibitive, because doing this processing already takes a pretty considerable amount of time. Yeah. And as far as the Rho HV, I haven't looked into why it looks so crummy. Yeah, so that's certainly something to look into. Okay, so that's the 20th. So you can see the line moves across, and then we're left with this stratiform rain. The 23rd is a supercell case. So let me just zoom to the beginning. So we have convection that forms along a dry line and then evolves into some supercells, which kind of wander about. Okay, and again, you can see where there's intense convection, high values of KDP, and also ZDR. Okay, and then the 24th is another supercell case. Yeah, so again, it occurs along a dry line, and then propagates out. I don't know why. Strange. I think this is actually for the 23rd. I'm sorry. I don't have the 24th. Apologize. Okay, so what do these KDP features actually look like? What do these things really look like. So basically, one of the things that we're interested in is deep updrafts. So if you have an updraft cell, an intense convective cell, that might be marked by liquid water reaching levels above the melting layer. So that's one of the things that we're looking for is where does liquid water reach above the melting level? And in this way, maybe identifying some of the features in a storm which are the most intense. What are the most intense sort of cells in the storm? And then using the rest of this radar data to get some idea of what's exactly going on there. Some idea of the microphysics of it. And in addition, getting some idea of basically, in general, what these things look like so as to determine observational targets that we can then use to compare to model simulations. So we figure out what nature looks like, and then we see if the model does something similar. Okay, let's see, I think I can go back here. Yep, so. Okay, so in general, right, as I said, we're going to analyze strong updraft cores. And this is all being done with this fabulous new open source software, PyArt, which is being developed by some of the people at ARM. And it's Python ARM Radar Toolkit. So this is free, it's open source. You can download it now and start analyzing radar data instantly. Whereas previously a lot of these things were sort of proprietary to various research groups. This is new frontier of software, scientific software. So as I mentioned, one of the ways that we're going to look at this is by looking for strong updraft cores by the presence of liquid water above the melting level. And so we can look at, for example, KDP, which is an indication of rainwater, and see if we see KDP columns sort of extending above that melting level. Okay. And we want to look at relationship between polarimetric variables. And also with updraft strength, we have the 3 Doppler analysis using 3 radars to get a 3-dimensional view of winds to see what the relationship is between the signals that we observe and wind speed. Okay, and then just assess consistency and variability of observed patterns. And in that way, sort of get an idea for what are consistent, robust features of nature that we want to observe in our models, where we want to see our models reproducing. And then also to have sort of a microphysical interpretation for what that is. Okay, so here's an example of KDP or ZDR columns. So this is a case on the 20th. This is reflectivity here, and so you can see the sort of line, the convective line here, and then these are slices through what I've identified as a KDP column. So you can see the reflectivity shoots up. That's because you have a strong updraft, which is condensing liquid water and producing rain and snow and ice particles as well. Okay, so we also see that with ZDR and KDP, you get a column extending up, and here's the melting levels at about 4, so extending considerably above the melting level. And that's our KDP column. And so we're using that as a proxy for having intense updraft. Okay, so, well, what do these things look like really? Well, one of the things that we've been doing is just looking at them 3-dimensionally to see what their structure is, to get a sort of qualitative idea for what these things look like in 3D. So what I've done here is just sort of picked out a few of these features. So 1, 2, 3, 4, 5, 6, and then try to look at see what they look like in 3D. And well, one of the things that sort of pops out is that some of these features tend to have an overhang in the north direction. So let's see. So that's north right there along positive y. And you can see that there's this overhang there. And that's a relatively consistent feature that we've been seeing. In addition, on this day, it seems like there tends to be a maximum of KDP, which is elevated. So comparing that to a different day, sorry. that to a different day, we see, for example, in this case, the maximum is at the bottom. So why is that happening, and how can we interpret that? We've been looking at, we've been looking at some bulk statistics. So
can you remind me what KDP indicates?
yeah, so KDP is an indication of the concentration of rainwater.
Okay.
Or it's related to the closely related to the concentration of rainwater. So, and we're using it as a proxy of strong updraft. So looking at its shape, its distribution will hopefully give us some idea into what the structure of these updrafts look like, and perhaps what sort of microphysical processes are occurring. Okay, so one of the ways that we can look at this is just by looking at comparing, say, our ZDR and our KDP. So let me just focus on this plot. So this is basically showing if you take a slice, or if you take your entire volume and you look at how much of that volume is above a certain threshold for KDP or above a certain threshold for ZDR, and then compare them. So in general, how much KDP are we seeing? How much ZDR are we seeing? In general, what seems to happen in this case is that the ZDR, which is in blue, seems to precede the KDP. So we tend to get ZDR showing up before we get KDP showing up. So in other words, we're getting big drops showing up before we're getting lots of rainwater showing up in these intense convective cells. This isn't always the case, and if we look at this day, the 20th, we see something which is the opposite. So we have a large signal of a lot of KDP happening before ZDR. So that's a little bit puzzling that we don't see a consistent signal. These are cases which could both be called squall lines. In this case, we have some idea that the reason why there's this disconnect is because, well, if we look at what's actually happening on this day, you can see that you get this intense convection, and then you get this huge stratiform region right here. And you can see that the stratiform region, this broad stratiform region, has pretty high values of ZDR. So, and that's happening after the most intense convection. So we have some idea that the reason why that lags behind is the sort of related processes of stratiform versus convective precipitation on that day.
For these plots, you take the average in the whole box?
So this is just looking at volume that's enclosed above a certain threshold.
But, yeah, okay.
I mean, you could also look at the average value, or the 95th percentile value, or something like that. One of the things that I found was that basically your prevalence of KDP seems to match the prevalence of updrafts, but the strength of each KDP column, i.e. once you have a KDP column, what your value of KDP is in there, doesn't seem to relate well to updraft speed. So I'm sort of more interested in that there are KDP columns that are extending above the melting level than what the specific value is within that KDP column. Yeah. At least for the moment. Okay, so that's the 20th. On the 23rd, we actually see something which was similar to the first plot I showed you, where you have ZDR preceding the KDP. And for the 24th, you also see that as well. You have ZDR preceding KDP. So exactly what this means isn't 100% clear until we do a little bit more analysis. And one of the challenges is that you basically have a system or a whole series of systems which are comprised of many different updrafts, and many different updrafts at many different points within their life cycle. So if you look at bulk statistics, very often you're sort of mixing mixing brand new thunderstorms with old thunderstorms, which might have completely different dynamics. So one of the ideas that we're having is to track individual cells. So here's one example of this cell tracking. So basically just looking for a single KDP column and following it throughout its evolution. So this isn't going to work, is it? Okay. So just following the cell throughout its evolution, and then looking at various statistics as this cell evolves in time. So that's still a work in progress. In addition, we are looking at the wind fields. So it's a little bit messy, but these are the vertical winds, where the red is updraft and the blue are downdrafts. And these are derived from the 3 Doppler analysis. The contours here are KDP, so they're indicating where these KDP columns sit, roughly. This is reflectivity, also with contours of KDP. If you're used to looking at reflectivity, maybe that's helpful. And so, well, from here it's a little bit hard to see, well, does our KDP sit in general in regions where we have greater updraft? And so, well, let's look more generally. This is another time step. There are 2 time steps. It's even harder to see here. And there are quality control issues with this 3 Doppler analysis, which are being sorted out right now. Not by me, but by one of our collaborators. So this should improve. However, you can still look at sort of some of the bulk statistics here. So if we look throughout our domain at, in general, how much air is going up? What's our vertical mass flux? And how much KDP do we have within these KDP columns? They seem to correlate pretty well. So in general, when we have a rise in vertical mass flux, we have a rise in these KDP columns. And that also matches up with average updraft speed. So as our updrafts become more intense, that seems to correspond to an increase in the KDP. So this is what I was showing you, that there is less correlation between the average KDP within a column. So the average KDP here is these dots here, and there's kind of a little bit more flat. Okay, so that's about it for now. There is a lot more that we're doing, and this is a big work in progress, especially in terms of just figuring out what these signals that we found really mean. So what's actually going on inside of these clouds microphysically that's producing the signals that we see? Is there a coherent argument for why we tend to see ZDR preceding KDP? So that's it for now. So any questions, I'd be happy to take.
Can you derive anything quantitative from those radar parameters?
Yeah. So the KDP, there are a lot of algorithms that use KDP to get rain rate, and similarly, you could use it to get rainwater content. And so that's something. So those derived fields can be then directly compared to model output.
So you've been talking about 4 quantities, and it's just one frequency. Right. So how many unknowns can we derive from 4 measurements?
Yeah, not too many. Yeah, and there's certainly an extremely large number of sort of free parameters in the natural system that we aren't going to be able to constrain. But I think the point is that, you know, in general you're getting it's like the move from black and white TV to color TV. And it's still not reality, but it's a better picture at least.
So, is it possible to separate your data into, like, you know, convective cloud versus stratiform? Because you show, like, you know, one kind of special case. It's like you said that's because of stratiform, and their physics might be quite different too.
So one way that I was doing that here for these plots. And this isn't necessarily the best way to do it, because there are certainly algorithms that kind of provide an automatic discrimination between stratiform and convective regions. But in this case, one of the things is this is basically the volume for the entire volume, the entire grid volume. But this is just for the region above the melting layer. So we don't really expect to see too much of a signal above the melting layer in the stratiform region. So basically what I'm asking is, do we still see the same signal just in these intense convective towers? And well, in this case, you certainly do. You see this peaking well before you see this peaking, and the peaks are about in the same place. There may be some indication that this leads this one a little bit, but it's probably too early to come to a conclusion on that. So, and you see that here as well. You see a peak in the KDP, where you see a peak in the KDP here. The ZDR is a little bit more noisy in this case. And here again, you have them following each other. So that's what we've done so far, but certainly using like an automatic algorithm to discriminate those regions might help with the analysis.
One of the goals, I think, what you do with N is also not to derive microphysical quantities from these measurements, but go the other way around. Have the model simulate basically these quantities that you measure, and then compare them.
Right.
And that kind of gets around this step of you have to retrieve microphysical quantities, and you have to add assumptions that that are not constrained. But so with all the assumptions that you make in the model, you can try to forward simulate basically the measurements and then compare them directly.
So what's the utility of
that? So then if they don't compare, then there's
you don't know why.
Yeah, no,
but I mean, this is also consistent with sort of the approach taken in data simulation typically, and you know, in the future, if you do want to derive some quantities of interest within the model, or constrain some quantities of interest within the model, your data simulation or your inverse modeling is going to be basically working in the observation space. So, and I mean, I guess.
Well, coming back to the why, it's like, you know, how sensitive are these things to the shape distribution of your droplets and your ice?
Very sensitive, yeah. Well, it depends on some. So the ZDR, for example, can be dominated by a few large drops. So it's reflectivity weighted. So if you have a few large drops that have higher reflectivity than a lot of small drops, you'll see a signal of the large drops, not the small drops. So that's one example. Yeah, certainly there's that sensitivity, but at least you're making no assumptions when you get the observations. And then any assumptions that you use in forward simulating are assumptions that you've already used for that modeling. So you have a consistency there where you're not adding in additional assumptions, such as you might if you're retrieving physical quantities.
An example would be the aerosol modeling, because people are pretty successful in matching the total optical thickness, and they do that in a zillion different ways. It just tells you that the measurements are not sensitive to what you need, period. And why is it just one frequency? Why not to use 10 frequencies? Why not to use multiple radars, to get like a tomographic view of this?
And we are hoping to do that in the sense that we are looking at the C band and the S band, and we're hoping to leverage the relative strengths. Whether we're going to do that in a very systematic way in terms of say forward simulating both frequencies, I'm not exactly sure. And certainly I've seen people use things like ratio of different of reflectivities from different frequencies to gain more information. I don't have any plans to do that now, but it's certainly something that that could be fruitful. Certainly, you have different information coming from each radar, and different radars are more or less sensitive to different things. ZDR on the C band is really hard to get because of differential attenuation, but it's more sensitive in KDP. So And then X-band also is sensitive to a whole different set of particles. So, you know, I think that should definitely be leveraged. Whether that's necessarily within the purview of what we're doing right now, I'm not exactly sure. I would love to do that.
The shape of falling drops, that's doesn't seem very difficult to model. Is it quite well known how basically dependent on size and fall speed relative to the air, then you can probably simulate the shape or not.
Yeah, I think that's well simulated. It's probably just the distribution that doesn't necessarily match reality. The drop size distribution that doesn't necessarily match reality.
Yeah.
I think the shape is probably more well constrained.
Yeah. Okay.
Any other questions?
So when you're comparing model and data, do you just have, so you run a large 80 simulation or something, and for each grid box compute the 4 quantities that are being measured?
Yep.
And compare those?
Yep. Right now, we don't really have any plans to take into account sort of beam propagation or attenuation along the beam path. It can certainly be done, but I think the forward simulators that we're doing right now are just like, you look at each grid box and you forward simulate what these things should look like, assuming that you have kind of a horizontal beam hitting the scatterers.
Okay. Thank you.
Okay.